Hello guys, welcome back. Today we are dealing with problems which are proof that physics rewards smart thinking. Now, if you love clever shortcuts more than long calculations, then you are going to enjoy this one. Now, let's start with the problems. Here, the first problem says they have given us two diagrams and both are square plates. So, the uniform square plate is placed on a horizontal floor when it is given an angular velocity omega, and that direction is also given here, about a vertical axis through one of its corners as shown in the figure 1. So in this case, if we give it omega, it says it stops in t1 time. It says here it takes t1 time to completely stop. Now the same square plate is given the same angular velocity to rotate about another vertical axis through its center as shown in the figure 2. Here they have changed the axis. The plate is same and they have given same omega. Now it says how long will it take to come to a complete stop in the second case. Now see here, to solve this problem, normally we would take there is downward mg, so friction will prevent it for rotation, and let's say the surface mu, there is coefficient of friction mu between the two surfaces. In that case, we can take at a distance r, we can take arcs like this, and the arc lengths will keep on varying throughout the length. So it will be a complex integration to solve the problem, but we will see a nice trick to it. The trick is called scaling principle. Now let's see how we use the scaling principle here. See, this is the solution. So first I have taken the square plate and they have said us we have given an angular velocity omega, right? Now I know that friction will stop it. So if I integrate friction over it, I don't know what value I will get, but I know it will be some number multiple of mu mg, as this one's mass is m and there is acceleration to gravity g downward. So net normal will be m into g. So friction, net friction will definitely be mu mg, but because of the integration and the arc lengths and all, there can be some other constant number which will get multiplied to this mu mg part. Because at what distance mu mg will act on an average, what distance mu mg will act, we don't know. So when I am writing torque equals to I alpha here, I have written the friction fold value mu mg, and along with it I have written a constant times L, because at what distance, the distance which will be the center of force, that is not known to me without integration. The net friction will definitely be mu mg, but if I want to, here I have to calculate the torque, right? Because the preventing torque, if it starts rotating this way, there will be a torque created which will prevent it, and that torque will be due to friction. I don't know what is the, I know the exact value of friction, but if I integrate, then friction on this element into the distance, and I have to integrate throughout the entire length. So I don't know what will be the result of that integration. So what will be the exact value of the torque, I don't know. So what I am doing is, I have written the friction. This will be the net friction mu mg definitely. Let's say this length I am taking as L. Then the point where the net center of force will be, let's say I am saying it is C times L. That's why this C I have multiplied. This C is a constant. And for similar diagrams, the ratio will be maintained. Like if I will divide it into 4 parts, which I have done in the second case, I have divided into 4 parts. So look, each smaller part now looks similar to this part, right? So, but as I have divided it, the each length will be now L by 2 here. So in this case, if I need to find the center of force, it will be C times L. In this case, the same distance will be C times L by 2. This is what I am saying as scaling. So if I scale it down, the structure, if I scale it down, the ratios will change. The constant values will not. Okay. So I have done the calculation for torque here. So torque equals to I alpha I have written. Again, I am not concerned about calculating the moment of inertia. I know that moment of inertia will be some constant k times mass of the object into length square, one dimensions square. That is what moment of inertia usually is, some constant times mass into a length square term, right? This is how moment of inertia's pattern usually comes up. So I have written torque equals to I into alpha. So now I have written alpha equals to mu gc, because m from both sides gets cancelled, mu gc by kl, where mu, g, c and k are constants. Now see, alpha is inversely proportional to 1 by L here. Now to stop it, I am writing omega equals to omega naught plus alpha t, because the torque, the alpha part is constant here. So here, if I put final omega is 0, then I get the time taken to stop it is omega by alpha, omega naught by alpha, sorry. It will be omega naught by alpha. So omega naught value is this omega here. If we put the value, we see that time is proportional to L, because all other terms comes to be constant. So here whatever the time is, I don't know the time value, but the time, if I check dimensionally, I see the time is directly proportional to the side length. The side length is L here. Now see, in the second case, if I divide the same diagram into 4 pieces, any one part, all of them will stop simultaneously, right? So instead of 4 parts, I can take any one small part and calculate the time for this small part only, this small part. So as I know कि time is directly proportional to the length of the square plate, then here the one each piece square plate has a length L by 2. So definitely whatever time this diagram used to take to stop, this diagram will take its half time. So don't think there are 4 of them and it will take 4 times, because all of them will stop together. It's like, let's say, one of your clothes takes 10 minutes to completely dry out if you keep it in sun, and if you hang 3 different clothes of similar material and keep everything same, the material same, the temperature same, the wetness same, and if you hang 3 clothes, then in 10 minutes only all of them will dry out, right? It won't take 30 minutes, because simultaneously all of them will start drying out. This is similar here also. Each 4 piece of the larger square plate will stop individually at the same time, and together also they will take same time. So instead of taking 4 of them, we can solve it by using any one of them, which will take half of the time. So it is t1 by 2. I hope you understand this. We see a new problem now. Now let's see this problem of electrostatics. Here they have given us, there is a solid non-conducting cube of charge density rho. So we have been given a cube here and its charge density is rho. It is non-conducting. Now they have said potential at center of the cube is V naught. So somewhere here at the center the potential is V naught, and it is asking us find the potential at C in second diagram and at P in both of the diagrams. So I have 2 diagrams here. The point P corresponds to the corner. So I can say here also the same point P is right here. So they have told us the potential at the center is V naught. They are asking what is the potential at P in these 2 cases. The first case is the whole cube, but in the second case, we have cut out a smaller portion of the cube, which side is length L by 2. We have cut it out. So find potential at these points and find potential at this point also. Now we will use the same scaling principle here as well. See how. Now, whenever we try to write the formula for potential, V equals to some constant K times Q by L, right? So dimensionally seeing, V is proportional to Q by L, charge and the dimension. Q and L are the charge and the dimension of the structure. Like kq by r, in case of a point charge it is kq by r, sorry, sphere. In case of sphere it is kq by r, where r is the radius. So here we have been given a cube, right? So cube's net charge I can write as rho into L cube, and length term is also there. So in directly I got the proportionality as V proportional to rho into L square. As long as rho same, potential is proportional to length square. So what does this say? This says, see, our larger cube has potential at the corner as V naught. So this entire diagram's potential here should be V naught if this corner portion is also present. But can I treat this bigger cube as 8 such smaller cube, whatever portion I have cut it here, no. If I repeat this kind of cubes, one cube here, one at this corner, one at this corner. So I'll get 4 cubes at the top half, similarly 4 cubes at the bottom half in this part. Again, I'll get 4 cubes here. So total there are 8 cubes which comprise of this entire large structure, right? And potential is the scalar quantity, so they get directly added. Now I say at the center of the larger cube, the potential at the center is V naught. So I can say this is 8 times corner potential of a smaller cube. I can say like this. So that means each smaller cube, the smaller cube, corner potential will be V naught by 8. Each smaller cube's corner potential will be V naught by 8. I hope you understand this. So that's what we have written. V at the center of the large is equal to 8 times V at the corner of small, because there will be 8 such small cubes and their corner potential will get added at the center here. So corner potential, one cube's corner potential comes to be V naught by 8. Now we know V is proportional to L square, right? So if I have a smaller cube of size L by 2, which is this one, this cube is of side L by 2 and this one's corner potential is V naught by 8. Then if I have a larger cube of potential, side is L, then according to this principle where V is proportional to L square, if length doubles, then potential becomes 4 times, right? So for the bigger cube, the corner potential will be how much? 4 times of V naught by 8, which is V naught by 2. So that means if I check this point P, here the potential will be V naught by 2. When the center potential is V naught, the corner potential is V naught by 2. How we got? I am repeating it again. I have made the scaling principle here. I assumed a smaller portion to be cut out. Actually, it is cut out here, but for now, if we assume we take a smaller portion, we know proportionality as V proportional to L square. At the corner of the large cube, there are 8 small cubes. So total 8 of smaller cubes potential net will be V naught. So one cube's corner potential will be V naught by 8. Now for a smaller cube's corner potential is V naught by 8. Then a larger cube's corner potential will be V naught by 8 into 4. Why multiply by 4? Because we already know V is proportional to L square. As the length becomes double, the potential will become 4 times. Now we know the corner potential. Now let's see what is the potential of C. Think right now, if we remove this portion, then potential of C will become how much? It will be V naught minus V naught by 8, because now there are only 7 such cubes which are present here. So for 7 such cubes, the potential at this corner will be 7 times V naught by 8. I hope you understood this. There are only 7 such small cubes are remaining, right? So here the potential of the 7 cubes will be added up. That will be 7 times V naught by 8. Now in the second diagram, potential at P, we can do like this, larger cube minus the smaller cube's potential at the corner. So larger cube's corner potential is V naught by 2. We have already calculated it. And smaller cube's corner potential is V naught by 8. That also we have already calculated. So subtracting these two, we get 3 V naught by 8, which is the potential at point P naught. So I hope you understood the scaling method. This is a different approach to solve very complex problems. Now, if you like this concept and you would like me to post more such ideas and problems, then don't forget to like the video and subscribe. It will definitely motivate me to keep creating more such contents. See you in the next one.